So welcome everyone for another seminar of the intercontinental seminar series of seminars. Today we have with us Maria Giovanna Dainotti from the National Astronomical Observatory of Japan. Maria got her PhD in Rome at the late 2000s, and then from there she went to Krakow, Stanford, several universities actually in the US. And since 2020 or 2021, she's been a permanent researcher at the NAOJ. And today she's going to talk about supernova type 1a, the Gaussian assumption, and their use together with other high redshift cosmological probes. Maria, the floor is yours.
So thank you so much, Costas, and for the committee for giving me the chance today to speak about the supernovae, the Gaussianity assumption, and their use together with other cosmological probes at high redshift, especially on gamma ray burst. So I would like to start first telling you about the Hubble constant tension and my work, recent work on this in this realm. So if we consider the probes of the early universe, we can see that basically all of them are around the these values that rely from 67 to 74. But if you consider the late universe, according to the probe that you have, basically the range of the Hubble constant, it goes even from 52 to the value of almost even beyond 80. So I wanted to show you this most updated plot to actually let you know that we still are in difficulty in determining what it is the true and intrinsic value of the Hubble constant because of these many measurements discrepancy. So we probably have read in the book certainly about all this huge discussion whether the Hubble constant is 50, whether it is 100, and then later the agreement was settled on 70, but nowadays again we have mainly this 4 to 6 sigma discrepancy between the values of the cosmic microwave background and from the Planck data and the value of supernovae 1a calibrated with Cepheids. Now, there are several possibilities about this. Either there are hidden selection biases in the supernovae parameters that we still yet have to be determined and even discovered, or a more fancy opportunity to see at this issue that there are difficulties in the current ΛCDM scenario, and therefore several theoretical explanations must be given to reconcile this problem. Now, in this series of papers, we have investigated this tension, and I will show you today this first two. And there are also theoretical interpretations. But very recently, actually yesterday, appeared on arXiv our new analysis for a master sample that combines several data. And once the paper is accepted, I'm very happy to put this analysis in the GitHub repository and also share with anyone. But of course, if someone of you is interested in using this master sample compilation, you can contact me privately, and we can exchange ideas and data for future collaborations. Now, I would like to start from the beginning, especially for if there are students present. So we start from the Phillips relation, and we go then to the three-parameter relationship. Basically, we have the relationship here that it is the combination of the peak magnitude in the B band, the absolute magnitude, the stretch parameter, the color, and the host galaxy mass correction and the bias correction. Of course, you may have seen this relationship in several flavors, with or without the bias correction, with the host galaxy extinction maybe embedded in the absolute magnitude if you consider Betulle et al. 2014, but this is the most updated relationship. And M is the absolute magnitude of a reference supernova in the Big Bang with the stretch equal to 0 and color equal to 0. And M is degenerate with H0. Now, if we consider the importance of this analysis and how we can calibrate with other probes, we need to understand how the chi-square is defined. Actually, the chi-square is the difference between the theoretical distance, the observed distance moduli that has been defined here by the proper quantities, and the theoretical distance moduli. And this is the uncertainty that includes actually both the systematics and that are part of the diagonal matrix and the statistical uncertainty that are part of the diagonal matrix and the systematic contributions that are the off-diagonal. So the difficulty that we had in our work to combine the master sample is that we needed to consider also the differences in the several chi-square definition when we built this statistical and systematic contribution in this C matrix. Delta mu is the difference between the theoretical distance moduli and the observed. And this is the equation that it is used where the theoretical distance moduli consider the distance luminosity theoretical that depends indeed from the cosmological models. In this analysis, we consider the two models, the lambda CDM and the flat W0 WA CDM model in the CPL parametrization, Chevalier-Linder-Polaski parametrization. We also used the baryoacoustic oscillation. In this case, the chi-square is considered as the sum between the contribution of the supernova and BAO. And in this case, we consider for BAO the sound horizon and also the degeneracy between the sound horizon, Hubble constant, and the parameter, the energy as a function of Z. Now, if we consider the theoretical models, again, because we are considering a flat lambda CDM and the W0 WA CDM, the radiation here is neglected and also the curvature is neglected. And here we have the equation for the dark energy density in the W0 WA CDM model. So in our case, actually, we consider that we fix the parameter of W0 WA to the fiducial value, and also for omega m, and we make H0 vary. The same for the lambda CDM model. We fix the H0 to fiducial values, and then we vary the H0. These fiducial values are taken from the several probes that we consider. In this paper, we use the Pantheon data, so the probes, the fiducial value of omega m is 0.298. For the Pantheon Plus, it is settled to the Pantheon Plus value, and so for JLA and DES data as well. Now, because we saw that there is a trend of the data that allows actually H0 to vary, we decided to consider a simple function for this evolution. And we consider this function as 1 plus z to the power of alpha. Now, here this H0 tilde is the value that H0 entails for redshift equal to 0. However, one could also argue that the H0 tilde that we obtain in our paper, both the previous one and this one, is not exactly at the fiducial value because indeed the supernovae are not exactly at redshift 0. Therefore, fluctuation about this value are indeed expected. And now, if we consider again this matrix, what we need to do is that to better evaluate this trend as a function of redshift, we would need to bin the data. And for the binning of the data, we need practically to understand which kind of bins analysis we need to do and also how many bins we need to consider. In this initial paper, we considered initially 3 and 4 bins because there was a prescription in the Skolnick et al. 2018 that to avoid systematic biases, we need indeed to have samples of hundreds of supernovae. Therefore, if you consider the Pantheon sample a collection of 1048 supernovae, if you divide in 3-4 bins, then you have this prescription of around 300 or so supernovae if you consider the equipopulation bins. Now, the equipopulation bins is something that it is good from the point of view of the statistical division among the samples, so you have the same number of supernovae in each bins. But from the point of view of the underpopulation and underestimating or overestimating the results at low and high redshift because you don't have the same volume, of course, another strategy must be tackled, and this is what we tackled in the recent paper in the archive, in which we consider instead the binning technique for the equivolume. So the volume is divided by, practically the sample is divided in log of z+1, which also mimics the evolution. Now, one point that one need to definitely pay attention for is the fact that when we consider fixing one parameters, we may have that because the parameters vary together, it can shift also the value of the Hubble constant. But this is not the case because we can see that if we consider 1, 2, 3 bins and the full Pantheon sample, the bin values, the value of omega n relies in at least 2 sigma when we consider the full Pantheon analysis. The same applies for 4 bins. Now, for lack of time, I will not show the new plot for this newly posted archival paper, but the situation is exactly the same. So if we consider our master sample and we divide the master sample in several bins and we reproduce the same, that this is the second picture if someone would like to have a look in this archival paper, we have the similar situation. Therefore, we can safely fix this omega n parameter and check how H0 varies. Why do we do that? Because basically what we would like to check is the evolution of the Hubble constant, whether or not it is not masked out by other evolution or other changes of the parameters. And this is given the sample size that it is small when we divide in several bins, it is a practical way to do that. We also compared our analysis with the Katsandisi and Peripopalopoulos 2020, and we obtained similar results for 4 bins. In their analysis, they used the M, the absolute magnitude, as a value that changes, but since M and H0 are degenerate, is the same as saying that also H0 is varying. And why then did we do the 20 and 40 bins? And by the way, in the new archival paper, we considered also an intermediate binning numbers as 12 and 20. We arrived up to 20 to show that this analysis is actually independent from the binning techniques and from the number of bins. We do the 20 and 40 bins because we would like to test the independence of the results on the binning choice and also on the binning numbers, because one can argue that if you consider a given number of bins and not another, this trend may not exist. Of course, there are fluctuations in the trend, and you can see these fluctuations in the very several tables that I'm presenting now and also in the archival paper. Now, if we consider this 3 and 4 bins in the ΛCDM model that it is presented in this left panel, and on the right panel you see the W0 WA CDM model, you can see that this trend is clearly visible. And here we consider the values of the absolute magnitude fixed to minus 19.245, because this is the fiducial value of M that corresponds to the fiducial value of H0 in the Pantheon sample. In this case, instead, we put the fiducial value of M equal to minus 19.244, because this is the fiducial value actually for the Pantheon sample in the W0 WA, and we have slightly different values. This is for the first bin we consider, and because when you go from 3 to 4 bins, actually you have some small variation. This is also the value of M that you have in 4 bins. Now, this evolution, as I said, is similar to this paper that considers the evolution only on M. Now, I mentioned that we wanted to consider also the 20 and 40 bins, and of course, here we can say that the variation of the data is more scattered, as we expect it to be, because you have less number of supernovae, in each sample. Basically, with the 40 bins, you have around 50 supernovae. You have around 25 supernovae, and with 20 bins, you have around 50 supernovae. Now, again, here we recalibrated the value of m for each bin, that you can see that it is slightly different between the ΛCDM model and the W0 WA model for this other number of bins. And the results are tabulated here. What we did was a simple exercise that entails the extrapolation of the Hubble variation, so this evolution at redshift of 1100, so the redshift of the last scattering surface, to claim this following answers. If this evolution keeps to be the same at all redshift, are we going to fix this problem of the Hubble constant tension? The answer is yes, because we obtain indeed all values that are compatible with 1 sigma with the values of the cosmic microwave background radiation from Planck, and we obtain a reduction in the tension that goes from 54% to 68%. However, in the new archival data, we have actually shown that there are two different samples, what we call a diamond sample and golden sample. The diamond sample has still this trend, decreasing trend, but this trend is similar to this analysis. So it is the order of 10 to the power minus 2. So it varies indeed from 009 to 0016. And the extrapolation to the very high redshift, indeed it is preserved to obtain the same value of the CMB. However, the golden sample does not reach the same values of the H0 at the CMB. And this can be due either to the fact that we are calibrating at 70, here we are calibrating at 73.5, that it was a request by the referee, but in the master sample, we decided to calibrate at 70 because among all the samples, the calibration was at 70, besides the Pantheon Plus, in which the calibration is at 73.05. But we also demonstrated that this calibration does not affect the results. Basically, this is still an open question. But by accounting for this evolution, we have 1.88 sigma tension, and so this is less than 2 sigma. Now, in this new paper of the master sample, we reached with the JLA and S data also value of these alpha parameters that is not compatible with 0, even at the level of 6 sigma. So it means that these results of this paper not only have been obtained for new samples and new analysis, but even they are even shown to be stronger in terms of this alpha sigma alpha that gives the idea of how many sigma you need to be away from 0 to consider this trend to be flat. Indeed, in the paper, we don't claim a strong existence of this behavior, rather an indication, but this indication becomes strong when we consider different samples. And of course, one can argue that if the trend exists, should exist in all samples and should exist regardless of the binning technique. And this is what happens here, but of course, fluctuation exists. And if you consider the 3, 4, and 20 bins for the W0, WA, CDM model, you have indeed the same situation. So you have similar alpha parameter that ranges from 008 to 0015 with given a scatter that makes all this measurement compatible in 1 sigma, and here you have that alpha sigma alpha is arriving at 1.9. And again, here you have a reduction of the tension that goes from 55% to 72%. Here we consider the difference as 1 minus XF final measurement XI, where XF is the actually ratio between the difference of the H0 tilde at redshift 0 and the value of H0 that it is by Planck, divided by the root square of the sigma uncertainty on H0 tilde that it is obtained by our analysis and H0. And we consider also the xi, so the initial value, as the calibration at C phase and CMB. And this is their uncertainty. Now, if we would like to visualize this, we can consider the different means and how these alpha parameters as a function of G of Z changes. This is for the lambda CDM model and for the W0 WA CDM model. Now, this is clear that if you have larger number of beams, you have also a larger number, larger uncertainties. And I already mentioned that we have similar results when we compare our results with the Katsan-Dissing and Peripova-Palopoulos, in which we have our value in blue and the other paper values are in red. And this is the values that we obtain for the first beam. Now, there are several possibilities with the colleagues. We investigated the testing of the Usavicki model. So if we had, for example, considered the Usavicki model to be the best approximation of this evolutionary trend, we would have obtained a flat contribution, but that it is not the case. And here we even changed several values of omega m to see how the Usavicki model would change according to these changes, but this did not solve the problem. So although we think that the gravity model could be a solution, despite this is not the one that will give us this evolutionary trend. Now, if we consider the value of, then we consider the follow-up analysis, the baryoacoustic oscillation, in which we consider 3 beams, and here the trend for the flat lambda CDM, including the BAO, it's practically similar. However, if you consider the W0 WA model, then you have a trend that it is steeper. Now, we were puzzled about these results, but we must say that once we consider this JLA data and DES data, and we combine with the Pantheon and Pantheon plus sample, then we also obtain this trend that it is very steep, as I said, around values that are almost 6. So this trend is practically recovered also only with the supernovae data if we consider other samples. But we still need to understand why this trend is present. Now, if we consider this analysis, we have actually not considered W less than -1, but also in future, we can consider phantom models. So in our analysis, when we consider in this second follow-up paper, we applied Gaussian likelihood. I mean, we applied Gaussian priors at 2 sigma around the value of W0 WA, not considering the phantom models, and also around the value of omega m. So to still see the trend, but yet to allow some variation in the value of W0, WA, and omega m. So there is another possibility that there is an evolution of the stretch factor that it was already claimed in the past by Nicholas et al. Permutter, and this should consider the fact that if the evolution, there is an evolution of the stretch parameter, and you can see that this is the probability, so this is heavy-tailed, this also influences the possibility to have an evolution in H0, as we have already shown in the previous formula of the distance moduli, that there is a dependence of the distance moduli observed with the stretch parameter via the alpha parameter. And now there is also another paper by Wojtak et al. 2023, in which we have 2 populations regarding the stretch and a clear trend of the Hubble residual increasing with the color parameter. So several people in the community are investigating these biases or possible hidden effects also in relation to the population, how this can contribute to different values of the Hubble constant. Now we can consider new theories, for example, the slow rolling, and this is what we did in a previous paper in 2024. this slow rolling theory seems to work better compared to Usaviki gravity. But what can we do now, and what we have recently done, is to combine the Pantheon, Pantheon plus JLA and DES data by removing the duplicated entry. So assigning priority to catalogs in the following order. So first the Pantheon, then the JLA, then DES, and then Pantheon plus as last. Why did we choose this? So the order priority has been chosen for comparison with the Pantheon plus, the Pantheon sample that was the first sample that we analyzed, so to match the trend. But another point is that in the Pantheon plus sample, there are more supernovae at low redshift. This is a problem because actually it allows then an overestimation, an overpopulation of the low redshift supernovae. However, we are very much interested to see what happens at high redshift. And in this paper in arXiv, we also added 2 high redshift supernovae at redshift 3 to check how this will change the trend. Of course, we need hundreds of supernovae at high redshift, and we can use the facilities of the Subaru and the future Roman observatory to obtain this very large sample of supernova 1A. And if someone of you is interested in applying for the supernova high redshift, we can prepare a proposal for Subaru for the open use. And as I said, the data will be available upon publication of this paper, and will be available for the GitHub. So for example, if you're curious to see with your own theoretical model, or if you're curious to see how you would match with your other data available, and you would like to have a much larger sample, so not the Pantheon plus that it is 1,701 supernovae, but a sample that it is practically almost 3 times larger, then please contact me and I'm happy to discuss how to use this data on. And I told you about the problem in this previous analysis regarding the equipopulation bins. Now we consider the equispaced bin in the sense that we consider the log of z plus 1, and we consider this log z plus 1 with a geometric space so that we can have that the z min, z max will allow this equipopulation, sorry, the equispace in the bin. And the results of this analysis actually are similar to the equipopulated bins, showing that regardless of the method of population of the bins, the results stay. But now, because I promised that I would tell you also what happens from another perspective, is the perspective of changing the likelihood. And indeed, the changing of the likelihood has been done also in this new master sample. So commonly, we assume Gaussian likelihood of the supernovae BAO, quasars, and GRBs when we consider the difference between the theoretical distance moduli and the observed distance moduli in the likelihood. But the problem is that, are all these valid? This is actually not the case, because when we consider the Pantheon and the Pantheon plus sample, you can see that the best distribution is the logistic for the Pantheon and the t-student for the Pantheon plus sample. Now, if we consider the Pantheon and Pantheon plus sample, you can see that the distribution are different and they are heavily tailed. Of course, one cannot check just by eye this, but we did check with the kurtosis and skewness test, and also the kurtosis plus skewness test, so that we can, all these tests fails. So it means that the normal distribution is not the best representation for introducing the likelihood. So what this means? It means that when you have the logistic distribution, you have this extra parameter that is the scale factor that is related to the variance by this equation. And in the t-student distribution, you have the gamma function, and the gamma function is also related to the degree of freedom and to the variance by this function. So in the analysis of the Hubble constant, we also may vary these new parameters. And of course, one could argue that we are increasing the number of parameters, therefore that's why we may have smaller uncertainties. But this is not the case because also we checked the A and B, AIC, the archaic criterion information and the Bayesian criterion information to check the validity of the model Gaussian versus non-Gaussian likelihood. And the non-Gaussian likelihood seems to be again a better representation of our data. Now, this is a visual inspection on what happens with the two different cosmological analyses. We have the Gaussian distribution that carries actually much larger uncertainty. Here on the left panel, we have the ΛCDM model for the Pantheon sample, and for the right-hand side, we have the Pantheon plus sample, again with the t-student distribution compared to the Gaussian distribution. So in both cases, indeed, we consider these differences. Now, what happens in terms of the reduction of the scatter? So we have that omega m, it is reduced by 43%. So this uncertainty goes from 0,021 to 0,012 and 41% for H0, from 0,34 to 0,20. And for the t-student distribution, it goes from 0,019 to 0,011 for omega m and 33% from 0,24 to 0,16 in the case of H0. But now the problem is that these are still supernovae 1A, so still at relatively low redshift. What happens if we consider these two additional scenarios in which we consider, for example, gamma reverse? So we have two possibilities. One, it is a simultaneous fitting, so we can fit simultaneously the correlation parameters and the parameters of cosmological of interest from GRB observation using also quasars and BAO, and we can calibrate with the low redshift probes, for example, the cosmic chronometer. And actually, we have been doing this with the Gaussian processes, but also we are working with Costas, Jackson, and Purba and Jürgen on this analysis by using artificial neural network and to check actually what are the results, including the cosmic chronometer. So we are in the phase of responding to the reference. So probably this paper also will be available soon published, but it is already present in this archival paper, so you can have a look. Now, the combination of the GRB, supernovae, and BAO, it shows in the case in which we have a simultaneous fitting that there is compatibility with the standard cosmological model. In this case, we indeed calibrate gamma ray burst on supernova 1A. So we can see that the H0 is assuming a value that are closer to 69.7. So it is closer to 70, and the question is that why it is happening, because the Pantheon sample contains this 1048 supernovae, and it has smaller scatter compared to the GRBs. Therefore, there are two weights that we have just seen in the previous slide, that it is the sum of the probes and the scatter. But because the scatter, and I will go a moment again to the equation, you see this scatter, the variance, the scale, it is on the denominator of this exponential, negative exponential, this weight more compared to the sum. Therefore, if we have the supernovae that not only are greater in number, but also they have smaller scatter, this means that then they weigh more. And even for quasars, even they are larger number than supernovae, but the scatter is larger in the luminosity relationship. Therefore, it is the supernovae that drives the results. And because of that, we consider different scenarios with the new likelihood, including the evolutionary parameters or not. So here, the no evolution function, this is what usually people use in the literature, do not assume any evolution. The fixed evolution, it means that we separately distinguish and analyze what are the evolving parameters for GRBs. And by the way, we used this G of Z function because it is the same function that we use for the evolution of GRBs and quasars. So this is mutated by the community of GRBs and quasars, and we transferred to the supernovae analysis. And we did also consider the varying evolution. So varying evolution means that we vary the parameters of evolution together with the cosmological parameters. So this treatment, the so-called varying evolution, it is the most complete one. And now I present this table for the non-flat lambda CDM model and flat W CDM model, but this analysis has been done also for the flat cosmological model. Now, we can see from this analysis that all the parameters, one are treated with Ln, it means the new likelihood, and Lg, it is the Gaussian likelihood. You can see from the new likelihood that all the parameters of omega m and h0, they have smaller uncertainties. And going to a table that will show you the difference in percentage, you can see that this difference is much more marked. Everywhere there is a minus, so it means that there is a decrease of the uncertainty on the cosmological parameters, and you can see that the varying evolution for the case of H0, it is arriving up to 0.29 or 30 in the case of this fixed evolution. And in the case of the flat WCDM model, we have a reduction up to 31%, and it is less marked, but still a trend of decreasing trend for Pantheon Plus. So the H0 central values are higher, as you have seen from the other table, and they are closer to the supernovae Pantheon sample values. Therefore, if you would like to bet your own money on what it is the most reliable value of H0, according to these results, you would bet two values that are closer to the values of supernovae 1A. And these results have been summarized in here, and we had also very nice press release for non-broader audience. We also mentioned about this second method in which we calibrate the value of the distance moduli on not supernovae 1A, because supernovae 1A is the one for which we would like to try to solve the tensions, but rather on cosmic chronometers. So the general idea is that you take one probe, which is not supernova, but it is enough close by as the cosmic chronometer. Then we consider the cosmic chronometer that are in the same redshift range of the GRBs. Then we identify a subsample of these GRBs. In this case, is 20 out of the total sample of 50 GRBs that are coming from the platinum sample of my correlation. And these GRBs constitute this sample for which you can consider this extrapolation. Now, this paper actually has been published in the Journal of High Energy Astrophysics, and when we consider the evolutionary effect, we have that the intrinsic scatter is 0.20. So this is comparable also with the fundamental plane relation for GRBs that has a scatter of 0.18 plus minus 0.019 when we consider also the simulation for the evolutionary parameter. So basically, this correlation, if you would like to use high redshift probe, it is the tightest correlation that you have so far in the literature, even considering other relationship that has been previously considered the tightest in the literature. However, that it is no longer the case because indeed the scatter of this also correlation grows according to the sample size, as it has been shown by these other papers. So what do we need more? So either if we would like to explore the high redshift universe with the GRBs, either we need new or tighter reliable relations, or we can increase the sample size having this cosmology independent approach via low redshift probes. And actually the new avenue is to try these artificial neural networks and also other means for machine learning to increase the sample. Indeed, we used also the inference for the redshift to increase the sample size, and also to have more physical interpretation about the connection between theory and the standard set for GRBs. Now, I would like to mention this series of papers that we had in the GRB field. This is with especially a PhD student that is now finally giving the final presentation of the PhD soon. So very successful endeavor with the many analyses that we obtained, and we inferred reliably the redshift of more than 150 gamma ray bursts. And actually in this latest paper that we do also the forecast for cosmology with this analysis, we have even a sample of 170 gamma ray bursts that are inferred. So this is important because this machine learning analysis does not entail the use of underlying cosmological models that therefore you can use for cosmology. And also this research attracted attention to the media, so we have several research press release. But one of the points that I would like to stress here is that we need still to be patient with gamma ray burst. And why so? Because you see, if we consider the more than 10 years ago, let's say now 14 years ago, we had this Conley et al. 2011 sample in which the precision of omega m was 0.10. This precision could be reached already 3 years ago if you consider machine learning analysis and the error bars that are divided by 2 with light core reconstruction. Indeed, in these days, we are working a lot on improving the light core reconstruction analysis, because then we can reduce the parameter, the uncertainty on the parameters of this relationship that involves the plateau-Mie relationship, but also we can apply to other relationship in the literature. And after we do that, then we can indeed reach this precision of the supernovae in a less number of years. If we consider exactly 10 years ago this precision of Betule, this can be reached in just 1 year from now, again using this machine learning. However, if we consider the Skolnick et al. 2018 precision, we would need to wait practically 16, 17 years from now. But this is like a very pessimistic estimate, because we are working now. We have published the catalog. We don't have in this analysis the Einstein probe estimates, and we have Swift, Svom, and Theseus. So we should not wait this number of years, and we should work more on these machine learning tools to improve our statistics. But so some people in the GRB community likes to say that the party with cosmology is over, because the golden age of observing high redshift GRBs didn't arrive fully as we expected. But in my opinion, that's not the case. We can extend this data with the Einstein probe. We can also consider quasars as good cosmological probes, because we did in a series of papers the hunt also for the quasar cosmology, because they are at high redshift. And indeed, in these very days, we are trying to use now the quasar for cosmology. And I would like to tell you a little bit about this, because I still have a few minutes left. So here we use a sigma clipping technique in the evaluation of the luminosity in X-ray and UV relation for quasars. So these sigma clipping techniques reduce iteratively the scatter of the relation, removing the outliers. So with this continuing clipping this analysis, we obtained a sample of quasar of 983, and we obtain a precision that it is the same precision obtained by Skolnick in 2018. Now, I would like to make a caveat on this, because this is the first time that quasars are standalone cosmological probe that yields such a tight constraint. However, one could say that this reduction of this measurement is due to the fact that maybe the sample can be biased to this due to this sigma clipping technique. And for GRBs, I followed another approach. I consider the platinum sample as the ones that have very clean light curve with no flares in gamma ray bursts. So the technique was different. Therefore, we decided to consider another technique instead of the simple sigma clipping, also the Huber regressor. The Huber regressor technique, indeed, it has the advantage that can select naturally the outliers, and we don't have to establish this sigma clipping technique that can actually render this Gaussianity assumption compared to the best fit not valid anymore, although we also put this into the sigma clipping technique as a further measured. In this case, we have a sample that it is slightly larger than the previous one with 1,132 quasars, and the sigma intrinsic dispersion is 0.22 versus the original 0.29, so it's 24% less. And the omega m, it has a precision of 0.089, so it is 4 times larger compared to the precision of the Pantheon sample. So still it is an improvement, but not as much as the previous analysis that we have considered. And here it is the analysis of omega m as a function of this parameter. Now, we were not happy yet about this analysis, and we decided to consider another analysis that would again consider the practical sample of 2,421 quasars, and in this case we use another binning technique, that it is the bin size maximization technique, which enables an enhanced bin division in which the redshift of quasars, the high redshift of quasars, are maximized. In this one, we consider the Thielsen regressor technique, which is even more powerful than the Huber regressor technique. And in this case, the sample size is 1,253 quasars up to redshift 7.54, with an intrinsic dispersion of 0.096. So basically, this is even 68% less than the previous total sample of 2,421 quasars. So in this case, the precision determined is at the level of 0.064, so it's 3 times, not 4 times, larger than the one, less than 3 times larger than the one of Supernovae Ia with the Pantheon sample. Now, how can we distinguish between this sigma clipping technique and the value of omega m and their uncertainty? So you can see that if we have smaller number of quasars, this sigma remains roughly the same, but of course it is a counterbalance. We need to have more data because of the likelihood. You remember the sum of the number of sources, but also we need to have a smaller uncertainty for this variance, and therefore we consider that this around 1,000 of quasars would be the best compromise between high precision and larger numbers. So the optimal sample is 1,253, which is around this point. Now, and this is the variation. This is how the sigma clipping technique varies. So it means that the more you are clipping the sample, you see the higher would be your omega m, because no, the more your sigma clipping is higher, it means you have a larger sample, and therefore this omega m is larger. Now, also interestingly, in this analysis, we saw that there was deviation from omega m, as you have seen in the other point, and we investigated this deviation also with f of r theory of gravity that can consider, in fact, an evolution also in omega m. Now, as I said, the story just began, so we need to check also the decreasing trend of the Supernovae Ia Pantheon sample with the nuclear likelihood, as we have done also for the master sample, and we can consider also as a next step also the BAO and the data from this collaboration, but we have also added in this master sample also the constraint for shows analysis. And actually, the good news for the GRB side is that we built the largest optical catalog to date with a sample of 535 gamma ray bursts in optical. Then we are going to use that sample with more GRBs with optical afterglows to enlarge our platinum sample. And also, if you would like to have also data from reconstructed light curve to improve your prediction for cosmology, please contact me. And also another analysis that we are tackling is to try to match the subset of GRBs with the magnetar model. So if the plateau emission is pumped by magnetar, then we are able to consider a given magnetic field and spin period. That could be the good one to identify a subsample of gamma ray bursts that can be used better as cosmological tools. And now I would like to just use my last minute, I guess, to give you some announcement. So there are, well, this is a usual deadline for the 1st of August, but there are also for the JSPS postdoctoral fellow for 2 years at NEOJ, but also I'm editor of the special issue of the gamma ray burst in multi-wavelengths, a theory, observational correlation, and GRB cosmology. So if someone of you is interested, the deadline is officially the 31st of January, so it's in a few days, but we are planning actually to extend officially the deadline by the end of February or middle of March. And even if you don't have a specific paper that it is fitting exactly in the gamma ray burst multi-wavelengths analysis, but it is also related to the Hubble constant tension and you are using gamma ray burst, then please feel free to contact me. And for the people that are invited, we have a few waivers still left, so there is free of charge. And there is no limit in page, so you can have a long review or a short review. So if this is something in your plan, please contact me. So thank you very much for your attention.
Thank you very much, Maria, for the very nice talk. In which journal is this special issue?
So this is the Galaxies. So Galaxies now this year has reached the impact factor of 3.2. So it was higher than the past years. And I also recently became not only editor of this special issue, but I'm also editor of the journal. So in case someone is interested, maybe even not submitting in this special issue, and you would like to have some special discount, also please contact me for that, and I will be happy to provide.
Great, thank you very much. Are there any questions from the audience? Okay, if not, I have some. So
yes.
Yeah, regarding this the quasar analysis that you showed us here in the last few minutes, like you showed that you use like the sigma clipping technique, the Hubble regressor, the TLSN regressor. I mean, and I wanted to ask, like, is there any like qualitative tool that can tell the difference, like not the difference, but like which one of these different methods is more reliable, let's say, or more yeah.
Yes. So thank you for your question, because we had brainstormed quite a lot inside the group about what could be the best technique. So this is sigma clipping technique because it is based mainly on what it is the sigma away from the best fit relation. And then it depends on the particular sample that you are considering. However, and it does not naturally preserve this Gaussianity, that it is this Anderson-Darling test that you would do between the data and the best fit to check for normality of your relation. However, well, we included also this condition, but however, the Tilson and Huber regressor, especially the Tilson technique, would have already included this Gaussianity check when the outliers are considered. So basically, the outliers in the Tilson and Huber regressor are picked automatically by this iterative procedure, that it is already included in, let's say, in the package that we use for, you can have in R, we use in R, but you can also find in Python. However, this sigma clipping technique, we do this removal of the outlier basically by hand, choosing this value, while in the Hubbell regression and Tilson, the outliers are weighted, are not actually removed, but are weighted differently. So I would say that this Tilson and Hubbell regressor are more powerful in terms of statistics, but also it depends on the analysis that you would like to have and the results that you would like to reach, because in principle, what we do in this analysis is that we have these outliers that are identified. So the outliers with the Hubbell and Tilson are weighted differently. However, we remove these outliers so that we reuse this new sample to obtain then the quasar cosmology. So eventually, we all in the three methods, we are going to remove these outliers, but we use different techniques. So I would say that Tilson is the most, how to say,
trustworthy.
Most trustworthy and reliable, but also these other two are good to be used. And you can see that with the sigma clipping, basically we obtain the most promising results, because with the sigma clipping, you can obtain already directly this standalone probe for other similar.
But you chop the sample by hand, right? So you chop the outliers by hand. So yeah, I guess
not exactly by hand, but by defining this distance of the data point, the outliers, to the best fit line.
I see. Very good. Thank you.
Thanks for the question.
Any other questions? Yeah, I guess most of the audience is more theoretical, so
okay, I see.
They might
well,
have
there are a
been...
few slides of theory, but my target is more on the observation, so that's
Let me stop the recording. Maybe they're shy to